Thanks for tuning in. Again, my name is Patrick Freeborn, and although I'm the one presenting today, I do want to acknowledge co-authors Matt Jolly, who also works here at the Fire Lab, Mark Cochran from the University of Maryland, and Gareth Roberts from the University of Southampton. So just to give you a heads up, I'll begin with a brief overview of fire diurnal cycles. I'll then give kind of what I consider a lightning talk about MODIS with respect to wildfire applications. And just to define that acronym up front, MODIS is the Moderate Resolution Imaging Spectral Radiometer, and it's a pair of satellite sensors with active fire detection capabilities. In part 3, I'll present some results. I'll summarize where and when MODIS is most likely to detect nighttime fire activity, and also present some CONUS-wide trends. So this is one of my favorite charts. It's taken from Simard's 1991 article in the International Journal of Wildland Fire. On the left vertical axis, we have spatial scales ranging from a point and then expanding all the way up to the planetary scale. And then the horizontal axis, we have our temporal scales ranging from an instant all the way out to the long term. Now, fire diurnal cycles, by definition, have a very specific time scale, 24 hours, right? But there's other temporal metrics out there used in wildland fire science that are a little bit more squishy. For example, residence times can range from seconds to minutes to hours, depending on the fuels, or depending on whether you're just talking about flaming combustion or the entire combustion history. The burn period is the time of the day when fires spread most rapidly, and that resides within the fire diurnal cycle, doesn't it? Fire lifetimes can range from hours if they're quickly IA'd, all the way up to weeks and months. The fire season, depending on the climate and the fire regime, can range from weeks to months. And then beyond the fire season, we got fire return intervals, which can range from years to decades or even longer. So when I think of fire diurnal cycles, I think of them in the similar terms as I do the fire season. And so when somebody mentions the fire season length, I kind of shrug my shoulders because I don't know exactly which one they're talking about. Talking about the fire weather season length, the fire activity season length, or the fire management season length. And like I said, I kind of think of diurnal cycles in the same fashion, that is in terms of fire weather, fire activity, and fire management. And so unless there's a frontal passage or something of that sort, the diurnal cycle of fire weather is mainly determined by the incoming solar radiation. And so on the left, we have a map of a predictive service area in the Southwest GAC. And within that PSA, we've got 4 remote automated weather stations. And if we average those measurements collected at the RAWs, we can get a diurnal profile of the incoming solar radiation shown on the right. Along the horizontal axis, we have time of day. On the far left is midnight, in the middle is noon, and on the far right, we have midnight again, such that the gray shaded out areas indicate the nighttime. And for future reference, those dashed vertical lines indicate the MODIS 4 times daily overpasses. And so a takeaway note for this diurnal profile is the peak of incoming solar radiation occurred at about 1 p.m. local time. And then air temperatures in red are coolest, and then relative humidities shown in blue are highest just before dawn. And then as the sun rises, the incoming solar radiation heats the Earth's surface, which causes the air temperature to rise. And with increasing air temperatures, we have decreasing relative humidity. And those trends continue even beyond the peak of incoming solar radiation because the Earth's surface is still absorbing heat. Up until a point where that solar angle is shallow enough to where the incoming solar radiation can't replenish the outgoing long wave radiation. And so those trends flip, you start to get decreasing air temperatures and increasing relative humidities into the night. And so fuel moistures respond to changes in temperature and relative humidity. And the solid green line is the trace of fuel moistures for 1 hour fuels with diameters up to 1/4 of an inch. And those are fine dead fuels. They respond the quickest to changes in atmospheric moisture. And you can see that just after sunrise, those fuel moistures start to decrease. 10-hour fuels are a little bit larger with diameters ranging from 1/4 of an inch to an inch. And you can see they respond more slowly. They're lagging behind the 1 hour fuel moistures. And then the 100-hour fuels are the largest shown on this plot, and they didn't fluctuate at all during that 24-hour period. Now, provided there's an ignition or there's a fire already burning on the landscape, the diurnal cycle of fire weather translates into a diurnal cycle of fire activity, as captured here with geostationary observations from the Severi instrument. Now, I made this slide several years ago when I was studying African biomass burning, but I kept it in here because I think it highlights the point very well. On the animation on the left, those white dots indicate Severi active fire pixels, indicating the locations of hotspots across Africa. And then on the right, we have a diurnal cycle of fire radiative power, or FRP. And for the time being, just consider FRP as a combined metric of both the fire size and intensity. And so what we see is we have low fire radiative power at night until the sun rises. You get decreasing fuel moistures, which results in faster spread rates, higher fire intensities, larger instantaneous active fire areas, until you get to a peak in FRP, and then it begins to decay as the sun sets and then tails off into the night. And so with the diurnal cycle of fire weather and fire activity follows the diurnal cycle of fire management decisions, and specifically what to do or not to do during a night shift. Right, there are tactical advantages to conducting nighttime operations. With those cooler temperatures and higher RHs, it may be easier to conduct burnouts. You may have more opportunities to go direct. If you're mopping up, it may be easier to see the embers and the open flames. And it's always good to be able to catch those spot slopovers and rollouts before the next burn period. But with all those opportunities comes trade-offs, right? Night shifts are accompanied by additional risks to firefighter health and safety. And the first bullet point there is actually a watch out situation. You're in country, not seen in daylight. And that second bullet point is one that I always have in the back of my mind, is that when you're working in the dark, it's going to be more difficult to access, treat, and then evacuate an injured firefighter. These are all important considerations to take into account during the decision-making process, but sometimes the nighttime fire behavior is so extreme that your decision space is essentially reduced to ensuring public safety. Now, I didn't even have to look for an article like this as an example. I found this last week when I was browsing our local news website, and it's been a year since the West Wind fire ran into the town of Denton, Montana. And there's two excerpts in this article I wanted to point out. It says, I got a fire call at 11 o'clock November 30th. That's 11 o'clock p.m. And the other excerpt is, some families evacuated the town on the night of November 30th. So it's media coverage like this, which is just one source of indirect evidence for increased nighttime fire activity. There's also fire reviews, like the Chimney Tops 2 fire review. There's some really cool scientific reporting out there. One, Climate Change Wildfire Risk Lurks in the Dark, was published in Scientific American in 2020. That's a really good article. Obviously, there's peer-reviewed journal articles, but a lot of those really just address the nighttime fire weather component. One source that we've had success with in the past are ICS 209s, which are incident status summary reports. And on those reports, there are fields where you can type in comments about fire weather and fire behavior observations. And I think these reports go back to 1999, but the nice thing about these reports is they're stored as Access database files. So you can actually crack open those files and query and scour for keywords like night or nighttime or overnight, which is what I did here for the Soberanis fire. And from that, you can compile a timeline of nighttime fire weather and fire behavior observations. This is practical for a single fire, right? When you got the time where you can take care and carefully read the comments and make sure you're interpreting them in the correct context. But this really isn't practical if you're talking about hundreds or thousands of wildfires. Instead, what we were looking for was a long-term consistent data set that we could use to quantitatively characterize the spatial and temporal distribution of nighttime fire activity across CONUS, along with any associated trends. And so the MODIS active fire product fit that bill. Why? Because MODIS provides global coverage at 1 kilometer spatial resolution, and it's been collecting observations 4 times daily since 2000. So MODIS isn't just a single instrument, but it's a pair of instruments flown on 2 near polar orbiting satellites, Terra and Aqua. Okay, both Terra and Aqua fly at an altitude of 705 kilometers. And if you notice, this animation on the left is an example of the Terra orbit. And so all those polar orbiting satellites do is fly around and around and around in the same orbit as the Earth rotates underneath it. And so MODIS is a scanning imager. As Terra makes its orbit, MODIS is continuously scanning and collecting a 2,300 kilometer wide image swath of the Earth's atmosphere, land and ocean surfaces. And this is an example of the Terra MODIS daytime overpass, which means it's in its descending node. That is when Terra flies over the equator at 10:30 a.m. local time, it's flying from north to south. And you can imagine that Terra is going to continue flying southwards over the South Pole and then travel northwards on the opposite side of the globe until it comes back over the North Pole. And 99 minutes later, it completes 1 orbit. And so during that time, the Earth is rotated 25 degrees, and therefore the image swath is shifted to the west. And you'll notice there's gaps in the swath at the equator, but those swaths converge at higher latitude. So you get near complete coverage of the continental United States in 2 consecutive swaths. Another way to visualize the Terra orbit is if you're wrapping a string around a ball while you're rotating that ball. And here we have the Terra ground track, just shown in a different projection. And Terra MODIS has already collected images of CONUS during the daytime in its descending node. And what this is showing is 12 hours later, Terra flies back over the same ground locations, but in its ascending node. And the ascending node is the nighttime overpass. And so when MODIS flies over the equator at 10:30 p.m. local time, it's traveling from south to north. And whereas during the day, MODIS can collect visible imagery because there's reflected sunlight, this is an example of a long-wave thermal infrared image. So if you look at a single point on the Earth's surface, specifically the Alpenrose in our predictive service area, and we look at the plot on the right, along the horizontal axis, we have dates ranging from June to the end of July. So essentially 2 months of overpasses. And then the vertical axis, we have the time of day. Midnight on the bottom, noon in the middle, and then midnight again at the top. So what we see is Terra MODIS flies over the Alpenrose twice, once just before noon and once just before midnight. Now, keep in mind that's Terra because MODIS also flies on board Aqua. So in combination, Aqua MODIS and Terra MODIS fly over the Alpenrose or any location across the United States 4 times daily, twice during the daytime and twice during the nighttime. So now that we've looked at the overpass schedule, let's have a look at some of the imagery that MODIS collects, and specifically with respect to the active fire detection algorithm. This is a 5-minute granule, so-called because it started image acquisition at 1820 and finished at 1825. And if we zoom in on Payson, Arizona, we see a MODIS true color image of the Willow Fire burning on July 3rd, 2004. Again, since this is a daytime overpass, MODIS collected visible imagery. And there are fire detection strategies out there that are trained to look for a smoke plume in order to identify the location of a wildfire. But most active fire detection algorithms rely on thermal imagery. So this is the exact same scene, but captured in the middle infrared channel at 4 micrometers. Again, just to drive the point home, whereas the visible imagery is based on reflected sunlight, thermal imagery is based on the radiant heat emitted from hot objects. And so each one of these 1 kilometer pixels has a brightness temperature associated with it. Okay, BT is the abbreviation for brightness temperature. And as you see on this color bar, brightness temperatures range from 300 Kelvin up to 380 Kelvin. Now there is a whole bunch of tests that the MODIS active fire detection algorithm employs. There's absolute tests, contextual tests, multispectral tests. And within those classes, there's a whole bunch of detailed subtests. But the only thing you really need to be aware of is that the ultimate goal of the active fire detection algorithm is to produce a binary mask indicating where a 1 kilometer pixel either contains a hotspot or it doesn't. So each one of these red squares is a 1 kilometer active fire pixel, indicating that that pixel actually contains combustion components. And then the black is the surrounding non-fire background. And there's basic information we get out of this mask, the date and time of detection, and the latitude and longitude. And in general, this process is just referred to as active fire detection, but MODIS also offers active fire characterization, okay? Associated with each of these 1 kilometer active fire pixels is an estimate of fire radiative power, and that's estimated in megawatts. And so on this color scale, the surrounding non-fire background, shown in black, is emitting 0 megawatts, okay? And then these white and really bright yellow active fire pixels correspond to the hottest brightness temperatures. And when you translate those brightness temperatures into FRP, those pixels are emitting upwards of about 100 megawatts apiece. And so if you take the FRP associated with all of these individual active fire pixels and you sum them up over the entire active fire area, on this particular day, during this particular overpass, the Willow Fire was emitting approximately 2,000 megawatts. So fire radiative power is the rate at which radiant heat is released from the fire, and it can be considered the product of the reaction intensity scaled by the radiant fraction and then multiplied by the instantaneous active fire area. And if you're keeping track of units, reaction intensity has units of kilowatts per meter squared, and the instantaneous active fire area has the units of square meters. I really want to emphasize that fire radiative power is not a proxy for fire intensity, okay? It's a proxy for a combination of both fire intensity and active fire area. So for example, if you have a 10 megawatt active fire pixel, it could be due to a low intensity fire that's large, or you can also get the same 10 megawatts from a high intensity but smaller fire, right? So if you double the reaction intensity and cut the instantaneous active fire area in half, you get the exact same fire radiative power. It's really important to understand that different types of fire can give you the exact same fire radiative power. And so just to drive home this concept of instantaneous active fire area, we can look back at the Willow Fire. And this is a 30-meter false color composite collected by Aster. And Aster is another instrument flown on Terra. And so on board Terra, you have MODIS and Aster, which collect images simultaneously. So in the background, the green is the unburned vegetation. The black is the recently burned area. The red indicates areas of active flaming, smoldering, and glowing combustion. And then on top of that Aster image, we have the MODIS 1 kilometer active fire pixels. Those are the yellow squares. And then the white outline is the final fire perimeter for the Willow Fire. So again, just to emphasize, the instantaneous active fire area is not the fire, it's not the final fire perimeter, nor is it the burned area. Okay, it's these red patches of active flaming and smoldering subpixel combustion components. And so one really important thing to recognize in this image are these red hotspots that you can see in the ester image, but that MODIS didn't detect. Okay, those are MODIS errors of omission, meaning that those hotspots were either too small or they weren't intense enough to trigger the MODIS active fire detection algorithm. And over time, the accumulation of MODIS errors of omission amount to a low spatial resolution detection bias, whereby MODIS can't detect a fire or a hotspot less than 1.5 megawatts. Another thing to realize is that at the very best, MODIS can separate vegetation fires from other static heat sources like volcanoes and gas flares and steel mills, right? But what it cannot do is it cannot distinguish and differentiate between different vegetation fire types. So if we want to identify active fire pixels that were triggered specifically by a wildfire, we need auxiliary data. And so we used the wildfire perimeters in the MTBS project. And for those of you familiar, there are prescribed fire perimeters in that MTBS database. We excluded those. We're only considering the perimeters for wildfires. And so the minimum mapping criteria for MTBS is 1,000 acres in the west and 500 acres in the east. So to get smaller wildfires included in that database, we supplemented MTBS with historic wildfire perimeters from the National Incident Feature Service made available through NIFC, which combined the MTBS and NIFS wildfire perimeters give us this atlas. And if you spatially and temporally intersect the active fire pixels with that atlas, it enables you to attribute the active fire pixels to a specific wildfire. In this case, the Soberanus fire, and this shows the nighttime progression observed by MODIS between July 22nd and September 28th, 2016. So to characterize field condition, we spatially and temporally intersected the active fire pixels with a 4-kilometer grid climatology of 1,000-hour fuel moistures derived from GridMet. 1,000-hour fuel moistures have diameters ranging from 3 inches to 8 inches. And so they respond very slowly to changes in atmospheric moisture, shown here on the upper right. And so what we used those for, it was to capture kind of these low frequency oscillating seasonality of the fuel moistures. Yeah, so this is a trace of the raw values for a single 4-kilometer grid cell in our predictive service area. Now, due to geographical variations in the local climate, there are some places across CONUS that never experience 1,000-hour fuel moistures as low as 4%. Also, there's locations across CONUS where the 1,000-hour fuel moisture content well exceeds 20%. And so to account for those geographical differences in climate, as well as the different relationships between fuel moistures and fire activity, what we did is we translated those raw values into percentile values, okay, such that the 100th percentile indicates the wettest conditions in that 4-kilometer grid cell, and the 0th percentile indicates the driest conditions in that grid cell. So to recap, we have 4 times daily MODIS observations between 2003 and 2020. And that covers CONUS at 1-kilometer spatial resolution. And associated with each active fire pixel, we have the date and time of detection, the latitude and longitude, the fire radiative power, whether or not it was detected inside or outside of a known wildfire, and the 1,000-hour fuel moisture content. So finally, some results. The first thing we did was take the MODIS active fire pixels and split them into daytime detections and nighttime detections. So on the left, we have a daytime mask indicating all the locations across CONUS where MODIS detected a daytime active fire pixel. And on the right, we have the nighttime mask indicating all the locations across CONUS where MODIS obviously detected a nighttime pixel. And so using the daytime mask, we were able to calculate an overall daytime proportion of fire radiative power. and that's calculated as the sum of fire radiative power detected during the day divided by the total FRP. Likewise, we calculated an overall nighttime proportion as the sum of FRP detected at night divided again by the total FRP. And so you'll notice that these daytime and nighttime proportions are complementary, so that when you add them up, they equal 100%. And the takeaway here is that overall, across CONUS between 2003 and 2020, if you consider all of the fire radiative power that MODIS detected, only 19% was detected at night. The balance, 81%, was detected during the day. Makes sense, right? You got lower fire intensities, you got smaller instantaneous active fire areas at night, you would expect a lower proportion of nighttime fire radiative power. Conversely, we took the MODIS active fire pixels and split them into locations detected outside of a wildfire mask, shown on the left, and then those detected inside the wildfire mask on the right. And so we calculated the wildfire proportion is the sum of fire radiative power detected inside wildfires divided by the total. And just to refresh your memory, the outside wildfires are all those active fire pixels detected outside of an MTBS or an NIFS fire perimeter. So those are all other vegetation fire types besides wildfires. So it could be agency conducted prescribed fires, it could be private broadcast burns, it could be private pile burning, but a lot of it's probably agricultural fires. So overall, MODIS detected much more radiant heat released from wildfires compared to other vegetation fire types. Next, we took all those active fire pixels detected outside wildfires and decomposed them into their daytime and nighttime proportions. And what you see here is that MODIS rarely detects nighttime fire activity during prescribed fires and agricultural fires, with a nighttime proportion of 3%. That doesn't imply that prescribed fires and agricultural fires completely extinguish at night. What this is suggesting is that those prescribed fires and agricultural fires that are burning during the day subside sufficiently at night to where they're too small or not intense enough to trigger the MODIS active fire detection algorithm. Likewise, we took all the active fire pixels detected inside wildfires and split those into daytime and nighttime proportions. And what you see here is that nighttime fire activity is not insignificant within wildfires. As a matter of fact, the nighttime proportion is 10 times that detected outside wildfires. So to come full circle, what we see here is that the overall nighttime proportion of 19% is actually a weighted average of 3% outside wildfires and 28% inside wildfires. So now that we've established the spatial coupling between MODIS nighttime active fire pixels and wildfire activity, we can look at the temporal coupling. And so on the left, we have a seasonal profile of monthly sums of fire radiative power detected by MODIS inside wildfires, shown in red. And what we see here is that the peak in the wildfire season occurs in August. And that's in contrast to the seasonality of prescribed burning and agricultural burning, which has a bimodal distribution with peaks in the spring and in the fall. And so if we take these two seasonal profiles, we can calculate the wildfire proportion on a monthly basis, shown on the right. So what we see here in January, February, and March is that prescribed fires and agricultural fires are dominating the MODIS signal. As we move into June, July, August, and September, the summer months, MODIS begins to detect increasingly more wildfires, so that the peak wildfire proportion hits 90% in August and then decreases thereafter. Shown alongside that seasonal profile of wildfire proportions in red is our seasonality of nighttime proportions. And you can see that those seasonal profiles are well synchronized. And indeed, the nighttime proportion is strongly correlated with the wildfire proportion. That's saying that as there's relatively more wildfires on the landscape, MODIS is detecting relatively more nighttime fire activity. And there's one month I do want to highlight, and that was September of 2020 out here, where nearly all of the fire radiative power that MODIS detected was emitted from wildfires. And during that same month, 40% of that total FRP was detected at night. To me, that's insane. And so I had to look at the SIT reports for September of 2020. And this is just a truncated list of all those large wildfires that were burning during that month. So not only can we differentiate nighttime proportions between inside and outside wildfires, we can further quantify nighttime proportions based on fire size. So in this plot in the upper right, we have nighttime proportions as a function of wildfire size. And so NWCG fire size classes A and B were combined to capture wildfires less than 10 acres. And then if you're not aware, fire sizes increase between C, D, E, F, and then G contains all wildfires with final fire sizes larger than 5,000 acres. And so in our plot, if you remember, we had a nighttime proportion of 3% outside wildfires. 19% was our overall nighttime proportion. But what we see here is with increasing wildfire sizes, we're getting an increase in the nighttime proportion of fire radiative power. And if you remember, our nighttime proportion inside wildfires was 28%. And 28% is also the nighttime proportion calculated within fire size class G. And so what that's telling us is that the nighttime proportion and the nighttime fire activity detected by MODIS is strongly determined by the largest wildfires. So why does the nighttime proportion increase with increasing fire sizes? Well, if we look on the right, we notice that the nighttime per pixel value of fire radiative power increases with increasing wildfire size. So it's really cumbersome trying to keep track of where and when active fire pixels were detected, whether they were detected in a wildfire or not, and if they were detected in a wildfire, what was the final fire size. So to some degree, we can kind of capture the effect of all those variables with the 1,000-hour fuel moisture content. Okay, this graph on the left, again, shows our seasonal profile of wildfire proportions in red and nighttime proportions in blue, which we saw a few slides ago. Behind those seasonal profiles, we see the distribution of 1,000-hour fuel moistures at the times and locations of those active fire pixel detections. So what we see is during January, February, March, and April, when we've got a lot of prescribed fires and agricultural burning out there on the landscape, those are occurring under relatively moderate fuel moisture conditions. Again, as we head into the summer months, MODIS detects increasingly more wildfires, and those, no surprise, are burning during the driest fuel moisture conditions. And on the right, if we look at those relationships directly, MODIS detects active fire pixels outside wildfires over a fairly broad range of fuel moistures, broad range of moderate fuel moistures. And then as we increase wildfire sizes, those fuel moisture distributions begin to narrow until out here in size class G, like we saw before, which was driving our nighttime fire activity, those active fire pixels are detected under a very narrow range of low 1,000-hour fuel moistures. So what's going on? Let's look at what's happening above the 50th percentile of fuel moisture, right? We got very low wildfire proportions, which means that MODIS is primarily detecting prescribed fires and agricultural fires during the day, but not at night. And so as fuel moistures decrease, those active fire pixels shift into wildfires. And so our wildfire proportion increases. And as we saw in the previous slide, as we get even further lower fuel moistures, those active fire pixels are shifting into the largest wildfires. As such, our nighttime proportions are also increasing as our 1,000-hour fuel moistures are decreasing. Why, again, are the nighttime proportions increasing? Well, as the 1,000-hour fuel moistures decrease, we're seeing an increase in the mean nighttime per pixel value of fire radiative power. Yeah, those active fire pixels are emitting more and more radiant heat. That's one part of the explanation. Another part of the explanation is that as 1,000-hour fuel moistures decrease, we get an increased probability of nighttime persistence. And here, nighttime persistence has a strict definition. It's the locations with a daytime fire activity are detected again at night. So as I alluded to before, above the 50th percentile where we have prescribed fires and agricultural fires, although MODIS detects those during the day, it's unlikely, if not never occurring, that MODIS detects those same locations again at night. In contrast, as we get the lower 1,000-hour fuel moistures where we have wildfires and increasingly larger wildfires, if MODIS detects a wildfire during the day, there's a really high likelihood that it's going to detect it again at night. And so finally, since 2003, MODIS has detected an increase in several nighttime active fire characteristics. In the upper left, an increasing trend in the annual nighttime sum of fire radiative power. In the upper right, we're seeing an increase in the nighttime mean fire radiative power per pixel. In the lower left, we're seeing an increasing trend in the probability of nighttime persistence. And then in the lower right, we're seeing an increase in the nighttime proportion of fire radiative power. So in conclusion, the majority of nighttime fire radiative power detected by MODIS was emitted from wildfires. And of that, the majority of that was detected in the largest wildfire sizes. Larger wildfires burning during drier conditions had higher nighttime per pixel values of FRP, greater nighttime persistence, and therefore had higher nighttime proportions. And since 2003, MODIS has detected CONUS-wide wildfire trends in several nighttime active fire characteristics. And lastly, although direct relationships between nighttime fire activity and meteorological conditions were not explored here, we're proposing that whichever conditions are driving large wildfires are also driving nighttime fire activity. And so that's all I got. Thanks all for tuning in, and thanks for Rachel for the invitation.
Yeah, thank you so much for that excellent presentation. I really appreciate you going through your methods and your data to help us understand how you got to these conclusions. So while I'm waiting for folks to type any questions they may have in the chat, I have a couple that I'll go ahead and throw at you. Okay. And you, the last point of your conclusion sort of got to this first question that I have, but I was just wondering, recognizing that these factors are interrelated, have you looked into parsing out how much of the increase in nighttime fire activity may be due to large wildfire-driven preheating and the creation of localized weather conditions versus a larger trend of climate change-driven increases in nighttime temperatures and drops in RH recovery? No, that's a very complicated question. I'm a remote sensing specialist. I'm not that savvy to try to carve up that question. I guess I was kind of anticipating a similar question. Right, so active fire pixels, MODIS is better capable of detecting larger wildfires. So it makes sense that we're going to see an increase in nighttime fire activity with larger wildfires. And quite honestly, just coming up with that relevation was kind of mind-bending.
And so, yeah, no, we haven't looked at any drivers. I mean, the only reason we used 1,000-hour fuel moistures was just to try to capture the seasonality of it all. But no, I guess at this point, the only thing I'm willing to conclude is that whatever may be driving these large wildfires are also driving nighttime fire activity. Yeah, hopefully it's kind of a sketchy answer, but no, I can't even attempt to carve that answer up.
Okay. Well, this next question is going to lean into it even more, so you can say the same if you'd like to. But John asked, have you looked at the correlation with El Nino or La Nina seasonal oscillations?
Nope, not at all.
Okay. Do you guys have any plans to dig into this further in the future to answer questions like that?
No, I follow Matt Jolly around, and yeah, I was lucky enough to slice off a couple hours a day to work on this project, but we got so much stuff going on here at the lab, and quite honestly, I don't know if I'm qualified to even address any of those really broad scale scientific questions.
All right. Well, if we have anyone in the audience, anyone who's listening who has an interest in digging into this further,
Yeah,
to.
Yeah, take the lead. Yeah, if you need any Modus active fire pixels processed, get a hold of me. I can crank those out pretty quickly.
And with that being said, I'll go ahead and drop your email address in the chat for anyone who's interested in reaching out afterward.
Thanks.
Well, I have a couple of other questions I'll just ask before we wrap up. I'm curious if you can extrapolate and think about what this research means for the wildland firefighting community, especially in the Western coterminous US, where wildfires are more precipitously increasing in size and intensity.
Yeah, not in real time. I don't think this has this work has any bearing on any real-time decisions that are being made. But like I said, I work a lot with Matt Jolly, and he kind of oversees the National Fire Danger Rating System. And if anybody's familiar with that out there, there are breakpoints and thresholds that you need to identify when you're writing up a fire danger rating operating plan. And so, and those breakpoints or thresholds are usually set up based upon the ignition of new wildfires. And so what we've been thinking about is maybe incorporating the Modus active fire pixels into that decision-making process. And so, can you still see my slides? Am I still sharing? So, maybe what we could do is bring those active fire pixels into Fire Family Plus, if anybody's familiar with that program out there, but import those active fire pixels into Fire Family Plus. And then you could use the nighttime fire activity to maybe identify some breakpoints and thresholds where you start to see an increase in the nighttime fire activity. So it'd be more like in the planning stage rather than the real-time stage.
Yeah, but it sounds like safety planning or danger planning and using this data could go hand in hand.
I think so, yeah.
All right. Well, the last thing that I'll ask you before we let folks go, again, bringing it back to the safety of firefighters and communities, do you know of any anecdotal or social science that speaks to the experience of wildland firefighters on the ground who have maybe experienced this increase in nighttime fire activity firsthand?
No, but interestingly, as our, I'll go back to this anecdotal evidence. I don't know if you saw it on one of these slides, but it was really cool. When our article got published in Remote Sensing of Environment last November, it got picked up by Wildfire Today. And you can see that in the lower left-hand corner. And so when they picked up that article, they put out a survey. And so it says, in the last 7 years on large wildfires, have you seen typical fire activity at night, more nighttime fire activity, or less nighttime fire activity? And it looks like there was 114 votes cast. and 83% of those, so this survey was poised to experienced wildland firefighters. And so the response was 83% more nighttime fire activity. So is that what you were asking, Rachel?
Yeah, that's exactly it. It would be interesting to see, you know, some more robust research.
Yeah.
Talking to folks who have been on the ground for, you know, 10, 20 years, just about what they've seen and what they've experienced.
Yeah. And, you know, for the past couple of years, everybody's been really talking about and focused on the fire season. And it's only recently that that we've been talking about nighttime fire activity. So hopefully this kind of thinking is just in its infancy, and yeah, and hopefully in the future we can get other smarter people thinking about this problem. So yeah.
Well, we're glad to have you on it, and
Cool.
appreciate you coming on and doing this webinar and sort of kicking us off with this kind of research and with these presentations.
Awesome.
So we'll give folks just another couple of minutes if anyone wants to drop their questions in the chat. Otherwise, let's see, Russell said they've been in wildland fire for 20+ years and would say that in the past 5 to 8 years, there's been a huge increase in fire activity during the nighttime hours.
Thanks.
So that's one first-hand account.
Yeah. Yeah, I don't, yeah, sitting here in my office, you know, reading incident status summary reports. Yeah, I don't really get the opportunity much these days to see nighttime fire activity.
Yeah. All right, well, we do have one more question. Eva asks, what might be the limitations, preclusions, or possibilities with the idea of using MODIS FRP as an archive for comparison with or validation for fire behavior model output?
Oh, I would say limited. Maybe in the past you would consider that, but that was before VEERS. The 1 kilometer resolution is very coarse, right? So let's look at that willow fire again, right? So those yellow squares in particular, right, on this side over here, these 1 kilometer squares are the active fire pixels detected by MODIS. And then in the background is 30-meter resolution imagery. And if anybody's ever run Farsight, you know those are 30-meter landscape fires or landscape files. And so I would say it's very difficult to use MODIS to evaluate a fire spread model. What you'd want to do is look for yeah, a finer spatial resolution active fire product.
And what was your recommendation for where folks might find that finer resolution data?
Oh, FIRMS. I can't remember what it stands for, but it's a NASA product. I'll you know what, I'll see if I can find the website.
Okay. Sarah just came in with another anecdotal story about
Cool.
nighttime fire activity on the Contreras fire in June of this year.
Okay.
It would be, you know, even if folks want to send their stories in, it's interesting to hear what everyone has to say. All right. Well, again, thank you so much, everyone, for logging on today, for listening to the presentation. Thank you again to Patrick for being here and giving the presentation and continuing to walk us through your research. And I really look forward to being able to work with you again in the future and keeping an eye on what you're doing.
Awesome. Thanks, Rachel. Thanks, everyone. Have a good holidays.